Hello, good morning, everyone, and welcome to today's webinar, Intelligent Conditioning Monitoring Using Digital Twin Models, where we will be talking about how advances in engine condition monitoring can improve vessel performance, extend engine lifespan, and even have positive impact on carbon emissions. We are joined by Kostas Milioulis from Datum Hawk, who are our sponsors, and he will be discussing how Datum Hawk is combining engine analytics with digital twin models to monitor engine health. Our moderator, Karl Jeffery, founding editor of Digital Ship, will be moderating the Q&A session that will follow our presentation. So please make sure you leave your questions in the dedicated Q&A box on the Zoom platform. Karl?
Well, thank you. So what we're going to talk about today is a new way of doing engine condition monitoring with one measuring device that's installed on the shaft and digital twin models. So this device is a shaft power meter. It's measuring the shaft torque, which is the force pushing the shaft to rotate, and the shaft rotational speed. And it's going to calculate the shaft power from those, and it can work out the engine cylinder pressures and get an understanding of the engine condition by comparing a simulation of the ideal conditions from what it's seeing now. Now, shaft power meters isn't a new thing, but what's new is the number of readings it can take. So Datum Electronics is about to release a shaft power meter that takes 2,000 samples a second instead of 10 samples a second with the previous shaft power meters. And all this data is getting analyzed on board, by the way. We're not sending lots of data over the SATCOM. So I'll explain a little bit more about how it works. So measuring the speed of the rotation of the shaft is quite easy. You've got a belt around the shaft and a device that reads how fast the belt moves. The torque is measured with strain gauges, which are fixed on the shaft. So that's sort of how much it's stretching as it turns. And if we know the torque, we can get the shaft power. So this device can be installed in 1 or 2 days without any dry dock. And Datum Electronics has a package it calls Datum Hawk, which includes the shaft power meter and the software. Now, this system could also actually be used to control the engine. So if we'd agreed a limit to engine power under the EEXI, we could use the data to make sure the engine doesn't go above this power limit. I'm not sure if this sort of virtual control system is allowed under the EEXI rules, but there's no obvious reason why it shouldn't be. Our speaker today is Kostas Milioulis. He's got a Master's of Engineering in Naval Architecture and Marine Engineering from Strathclyde University in Glasgow, where his thesis was designing a zero-emission ballast-free hydrogen carrier. And he's also worked in design and safety analysis of LNG fuel systems and marine engines. And now he's responsible for the research and development of intelligent diagnostics for marine engines in Datum Electronics. And unfortunately, you're not going to be able to see Kostas today. I'd like to say it's some secret reason that he's involved in a spy service or something like that, but actually it's because of a problem with the laptop. But I'd like to invite Kostas to give his talk. Thank you.
Thank you, Karl, for the introduction. Thank you, guys. I would like to thank the Digital Ship for sponsoring this event and giving us the opportunity to showcase our studies. I would like to share my apologies because I'm not able to show my face right now, as Karl mentioned, and it's only because some technical issues and nothing else. So I'm just going to share my screen, and that way you'll be able to see the whole screen without my face interfering. And so my name is Konstantinos Milioulis, and I work as the lead project marine engineer in Datum Electronics. And today I will be presenting to you our latest initiative, which is the concept of Datum Hawk. And in our mind is the future of intelligent engine diagnostics. This concept is a bit technical, so I try to keep the presentation as simple and as comprehensive as possible in order to keep only the essential information and what is beneficial for the vessel and the client, and not get lost into all the details. And without further ado, I will start the presentation. I will begin by introducing Datum Electronics to you, who we are and what we do. I will elaborate on the concept of Datum Hawk and what we have been working the past few months, and how this concept incorporates our latest shaft power meter, which is Datum Hawk ready, and how it makes clever use of digital twins and more specifically the crankshaft dynamics and the thermodynamics digital twin, to produce useful outputs for the engine condition and the engine health. And when talking about digital twins, what I mean is digital replicas of physical objects that we are able to simulate in a digital environment. Then I will present to you some case studies that we completed recently. I will also speak about the integration capabilities of Datum Hawk and how it can be incorporated to other systems on board. And I will conclude with an overview and summary of the benefits of our concept. So about Datum, we are located on the Isle of Wight. We produce and sell innovative torque and shaft power measurement solutions for the past 30 years. We are at the forefront in research and development of torque and strain measurement technologies. And we have an extensive network of resellers and suppliers in more than 30 countries. We are also involved in over 9 industries, including shipping, automotive, aerospace, renewables, and others. So what is Datum Hawk? Simply, it's an innovative approach in engine condition monitoring. It makes use of just one sensor, so it's a very cost-effective solution. It's comprised of our in-house developed hardware and software. The hardware consists of our power shaft meter, which is able to take up to 2,000 samples per second, to measure up to 2,000 samples per second. And the software is comprised of the crankshaft dynamics and the thermodynamics digital twins, which are replicas of crankshaft of the engine and the engine combustion process. It works by simply measuring first the instantaneous crankshaft torque of the engine using our high sample rate shaft power meter. We take these torque measurements and employ them in a self-adaptive algorithm that contains the crankshaft dynamics digital twin, which describes the crankshaft of the engine. And this digital twin is able to reconstruct the current in-cylinder pressures for each engine cycle. These pressures can then be compared against baseline pressures for a healthy engine via the thermodynamics digital twin. We can then quantify the differences and the engine health status through KPIs, key performance indicators. And we can produce a variety of different KPIs as required by the client. Now, a little bit more about our shaft power meter. At this point, I would like to say that we are already producing shaft power meter measurement solutions. And this is our latest iteration, which we aim to be commercially available in the next 3 to 4 months. It's being developed in a smart and environmentally friendly way, and we are currently in the process of gaining SPM certification and class approval from all major classes. It's a modular design, so it can be fitted to any vessel with any shaft diameter. It can be easily retrofitted to existing vessels. It can be recycled between vessels with different shaft diameters, and accommodations can be made with existing customers to upgrade to this product once it is ready. The technical features, the main technical features are that it's maintenance-free, which is important. It's tested up to 3,000 RPM, so it works for all engines. And as I said, it uses 2,000 samples per second instead of just 10 samples per second with our current shaft power meter solutions. The design is very simple. It uses a stator, which is bolted onto the frame of the vessel. And the stator gives power to the belt that goes around the shaft. There are strain gauges glued onto the shaft that measure the strain of the shaft and translate it into torque, thus measuring the torque. And this torque signal goes through a transmitter and a receiver to the control unit that contains a digital display, as you can see in the image. And the digital display showcases a variety of different measurements, including torque, power, and speed of the shaft. I will now elaborate a bit more on the technical side of the concept, starting with the crankshaft dynamics digital twin. It is basically a torsional model of the crankshaft of the engine, that simulate the crankshaft stiffness and damping characteristics. Before it's being first used in an engine, it requires calibration. And the calibration is a process where we come on board and we measure the in-cylinder pressure for all cylinders and use them as inputs into the digital twin, as well as information from the engine's torsional vibration study, like stiffness coefficients. It then simulates the engine's instantaneous crankshaft torque at the point of the shaft where the real shaft power meter would be installed. And the calibration is a process of trying to match the simulated torque with the measured torque that is taken from our shaft power meter. After the digital twin has been calibrated, it is utilized within a self-adaptive algorithm. What does this mean? Basically, it uses as input the high sample rate torque measurements from our shaft power meter and can then reconstruct the in-cylinder pressure for all cylinders. So it's a solution for measuring the pressure of the cylinders of the engine with just one sensor. And this is the main highlight, that we can use only one sensor to retrieve the in-cylinder pressure for all engine cylinders. Now, a bit more about the thermodynamics digital twin. Its characteristics are that it simulates the combustion inside the cylinders. It's available for all engines, including 2-stroke and 4-stroke engines. It reproduces the engine's performance in healthy conditions and at any operating point. And it can also be used to simulate the engine performance under different malfunctioning conditions. It also requires calibration, and it's easily done using the shop tests from the engine manufacturer. After its calibration, it can produce outputs that include vital information, such as exhaust gas temperatures, turbocharger speed, in-cylinder pressure, in-cylinder temperature, and others. And its main highlights are that a multitude of outputs can be generated. It can be utilized as a baseline to compare with a variety of measurements, and can be employed in tandem with the crankshaft dynamics digital twin to evaluate the engine's health status. Now, moving to the first case study, which is it was done for an Artiflex marine diesel engine, 2-stroke engine with 6 cylinders. The first step was to calibrate the thermodynamics model. So we start by using the thermodynamics model to calibrate them using the shock test, as mentioned earlier, for only one cylinder. And we derive the baseline performance for as good as new conditions for every engine operating point. We were then able to capture the in-cylinder pressure curves for all cylinders for as good as new conditions. And here you can see an example of the pressure curve for just one cylinder under different engine loads. After we calibrated the thermodynamics model, we proceeded to obtain the torque measurements using our Datum Hawk shaft power meter and use the torque measurements as inputs in the self-adapting algorithm that I described earlier that uses the crankshaft dynamics digital twin. We can then generate the in-cylinder pressure data for every engine cylinder. And it's basically, after that, it's a comparison between the baseline pressure and the measured pressure to obtain the engine health status. And in this case, the engine was at 92% of its full capacity. And as you can see from the first diagram on the upper left corner, you can see this is the torque signature curve of the engine as measured by our shaft power meter. It has 6 peaks corresponding to each of the 6 cylinders of the engine. But just by visually inspecting the diagram, it is not easy to ascertain which cylinder is underperforming and by how much. So it's necessary to use this information as input to the crankshaft dynamics digital twin and produce the in-cylinder pressures as outputs in order to compare them with the baseline pressures for a new engine. Now, the second case study was done for an early adopter of Datum Hawk, which is P&O ferries. It was done for a cruise ship with four-stroke medium-speed engines, and we used this concept to diagnose the engine shaft. For this procedure, we did an inverse process of the crankshaft dynamics digital twin. So instead of using the in-cylinder pressures as instead of calculating the in-cylinder pressures, we use them as outputs, as inputs, I'm sorry, and we simulate the torque and compare the torque that is simulated with the measured one that we get from our shaft power meter. We then use the stiffness coefficients of the shaft as variables to self-adjust them and correct the difference in torque. So just to elaborate a bit more on that, these two diagrams are torque signature curves of the two engines of the vessel. Each has 9 peaks corresponding to each of the 9 cylinders of the engine. And you can see with the red line, the measured torque coming from our shaft power meter. The dashed line is the simulated torque at the beginning of the process. And using the stiffness coefficients of the shaft as variables, they are self-adjusted in order to match the simulated torque with the measured one. And when the matching process ends, we have a very good understanding of the degradation of the shaft components. And in this case, we found out 21% and 18% torsional damper degradation in each of the engine shafts respectively. We also found out degradation in the couplings of the shaft. And the immediate implications of this degradation is an increase of torsional vibrations in the shafting system. And of course, a reduction in reliability. Now, the integration capabilities. Datum Hawk aims to offer many integration capabilities with existing systems on board. So if, depending on the requirement of each vessel, each client, we can produce live engine performance data that use as inputs other parameters, and we can produce displays that contain the vessel speed, fuel consumption, of course, power and torque. And there is a seamless integration with fuel flow meters on board for measuring the fuel flow that goes into the engine, so that a comparison of actual engine power produced versus the fuel delivered to the engine can be made, and thus calculating the specific fuel oil consumption and ensuring optimal engine performance and fuel cost savings. There's also reporting available through a report dashboard, and these reports can be either downloaded on board or sent directly ashore for studying. So there are many options, and these options can be adjusted to each individual ship according to its needs. And now for the overview. In its most basic form, Datum Hawk uses our latest shaft power meter solution that takes 2,000 samples per second with the digital twins to produce the engine health status. It's as simple as that. The high sample rate power shaft meter measures the instantaneous crankshaft torque, which is already a useful measurement on its own, and contains information for each of the cylinders of the engine regarding torque and power. And the crankshaft dynamics digital twin has the ability to gain insight into the cylinder's condition and perform shaft diagnostics. Lastly, the thermodynamics digital twin can be used as a standalone module to evaluate the engine's health. And the main benefit of this is that Datum Hawk does more with less. So we use a single sensor for engine monitoring, and it's a very cost-effective solution. The installation is very easy to do. It takes 1 or 2 days, depending on the case. it doesn't need to be, the ship doesn't need to be in dry dock. So it can be done, for example, when loading or unloading cargo. There is a high ease of integration with existing sensors, like fuel flow meters. And we aim to achieve integration with Datum's upcoming EEXI shaft power acquisition module, which will be a separate module regarding the shaft power limitations of the main engine. And overall, this is a predictive maintenance or condition-based maintenance strategy, as it allows the live monitoring of each cylinder to take place. We can identify the onset of degradation of the engine or the shaft, thus reducing downtime. And we can also identify engine inefficiencies and increase fuel savings. And this is the picture is an example of how the Datum Hawk interface might look like when installed on board the vessel. I would like to thank you for your attention, and I would like to welcome you for any questions you may have.
Oh, well, thank you very much, Kostas. That's great. So we've got a couple of questions coming in. I'll just ask people in the audience if you can put questions in the Q&A box rather than the chat box. And Thomas, if you could repost your question in the Q&A box. Just to set the context, do you want to say, I mean, how much does an engine typically degrade over its life? And so I guess people know this already, but they know about it faster with this. I mean, is it something like 10%, 20%? Is there some number you can put on that?
Depends on the individual ship that we are talking about, but in general, engines can degrade up to 20% over a period of 20 years. And the maintenance cost, talk about costs, are approximately 5%. Sorry. Yeah, but let's keep it to the degradation. Yeah, but 20% over the lifetime of the vessel is a nice clue.
Okay, and I mean, it must get maintained typically. I don't know much about engine maintenance, but I mean, it must typically get maintained. So companies would normally get up to the 0% over its lifetime, would they? Or I guess with a system like this, they come in sooner and do the maintenance work if they knew it was needed. Or?
Yeah, well, the aim is to, as I said, it's part of a predictive maintenance strategy and condition-based maintenance. So you will have the ability to see, to spot a fault in the engine or an inefficiency in the engine before the engine breaks. So we provide the ability to do the correct maintenance before a breakdown is happened. So thus reducing downtime and repairing the engine at an appropriate time.
Okay, no, that's great. Yeah, no, I just want to get a sense of the bigger picture. So we've got 4 good questions coming in now. Maybe we'll start with Thomas Sandbo, who's Senior Manager Fleet Connectivity and Automation with Wallenius Wilhelmsen. So he's asking about sending data into a cloud. I mean, you mentioned 2,000 samples per second, so you're not going to want to send all that to the cloud but you said you could send some reports to the cloud. Do you want to give some thoughts about how customers might send the data home?
So this is the first step. Datum Hawk will be commercially applied in stages. The first stage would be to measure the data on board, and the data processing is happening live on board. So the torque is captured on hard drives that are stored in the control unit of the shaft power meter. And the crew can access this information through the engine control room. And at a later stage, and if required by the owner or the client, we can provide SATCOM services, whereas we can send this data live 24/7 or when required for data analysis in the office. But these 2,000 samples per second, they're happening live, and the data is processed live, and the useful outputs are the torque and the power. And this can be accessed anytime by the crew, and reports can be generated that can be sent ashore. I don't know if this answers the question, but
Yeah, I think so. So Ralph Butcher, who's product manager with DNV is asking about APIs to connect to maintenance programs. Is that something you thought of yet? It sounds like it's quite a new product, isn't it? But
yeah, we haven't actually thought on that yet, but there's a possibility to. There's a high integration capability with Datum Hawk, so we aim to produce the Datum Hawk as a tool that can be used with many other systems on board and many other interfaces, like the APIs. So we don't know the details of that yet, but it is something that we can discuss and we can have a look into the future.
Okay, so Henrik Stribolt, who's a business development manager with MAN Energy Solutions, so he's also an engine expert, was asking about predicting the type of maintenance job. So I suppose this is showing the level of degradation. It's saying that you're not getting the cylinder pressure you thought you should have. You're not actually telling people what to do about it. That's sort of different. But if you knew about engines, you'd use that information to know. Is that a
the in-cylinder pressure is a good indication of the condition of the cylinder of the engine. So I think this information by itself is very useful. And what to do with this information depends on the specific case scenario. We can provide the ability to analyze this data ourselves and give reports back to the client. But the outputs of Datum Hawk will not show exactly what you should do. They will just provide data that can be analyzed and then derive the course of action. And this data, I think they are important data, like the pressures and other stuff that can be discussed. But yeah.
Yeah, but it's still enormously useful, even if it doesn't tell you exactly what to do about a problem. That it tells you there's a problem emerging, and you can talk to somebody about it.
It's a monitoring system. It doesn't give you the explanation. Explanation of how why this happens. It just allows you to see what is happening at that specific moment with data. So it will not give you guidelines as to what is wrong, how to fix it. It's just as a supplementary monitoring system that can be either be used for validation of the current monitoring system of engines, of new engines that have sophisticated monitoring systems already, or it can be used as a diagnostics procedure for older vessels that don't have many monitoring interfaces on board. So
yeah, and it's good. You can add it to any ship at any time, and it's not just new ships. So I think that's a
it can be. It's modular. The design is modular. The shaft power meter comes in a package. It's shipped to the client. It's installed on the fly. It has the ability. We can later change the shaft power meter to install it on another ship if it's requested. There are many options.
Okay, so we've got two questions from Rodion Denisyuk, who is CEO of iGauge in Paris, which is a sort of IoT sensor company. So he's asking about propeller and the bearings. Do you exclude them from the calculations? I suppose you do include them in the calculation. If the propeller is fouled, then you get less torque for the same. So I'm not an expert on this. You better answer this question. I think. Do you want to talk about the propeller and bearings?
We first of all, in terms of vibrations, the power meter, the measurements do not include any vibrations because there is an averaging taking place. So that's not about fouling. It's more about the effects on vibrations and ship movement, stuff like that. So vibrations do not have an effect on the measurements as an averaging takes place and cancels them out. As far as for the fouling is concerned, it can be taken into account, but when we install the shaft power meter, we calibrate it to be used for the specific engine. So it wouldn't be able to account for a fouling that happened before the installation, but it can provide useful data that can maybe reveal fouling of the propeller and the couplings later on. So
you get less speed of the less rotational speed for the same torque if you had fouling, I suppose, wouldn't you?
We have the ability to provide thrust information of the propeller, so you would be able to see a declining trend in thrust, thus assuming that the propeller is fouled. So this can be done.
Okay, so if we go to Ioannis Asimakopoulos, who's a PhD research fellow with the University of Southern Denmark, he's asking about color coding, which I don't actually remember seeing in your color coding for the why did you choose your color code? Did you put much thought into the color code, or don't know if that's so important?
Well, this is a question for the more for the engineers responsible for assembling the shaft. But yes, we have color coding for every cable, and we have analog outputs and digital outputs that can be directly connected to the engine control monitoring and to the engine control room. So yeah, I suppose we do have color coding.
You're talking about color coding for the KPIs. It must have been something on one of the charts I think you had. Did you, or different color codes? Yeah.
Do you mean color coding for the results or for the cables?
The results. Yeah, maybe that's not a. Maybe we'll go on to Nick Williams' whose question, shall we? He's talking about the Nick is asking about the flexibility to install on other sorts of vessels. I guess you can install on any vessel. They all have an engine and a shaft and a propeller, do they?
Yeah, we already install our shaft power meter solutions to fishing vessels.
Okay.
So
okay.
we can go as small as a fishing vessel to as big as an oil tanker.
Nick is a naval engineer with British Maritime Technology, by the way.
Okay.
I guess you have to have the initial model to know what to compare it with. Is that
Sorry, what was the question?
Well, to use on different types of vessels, you've got to have the initial model of how it looks like in the perfect condition, I suppose. Is that what you'd need to install on different types of vessels? Or?
First of all, the hardware installation. We would require the shaft diameter.
Okay.
In order to produce the shaft power meter for the specific shaft. So, but it's, as I said, it's a very modular design. So it has clips that can be easily retrofitted to another vessel. So there's the possibility of easily changing the shaft to another vessel. And in terms of software, as I said, can be calibrated. It must be calibrated for each specific engine, so each specific vessel. But there are limitless possibilities of where to use the concept, the Datum Hawk concept.
Oh, very good. So Artem is asking about a price. I know we talked about this before, and you're not involved in the sales directly, but are you able to share anything with us, or is it you'd rather keep that for private discussion?
I can provide some indications of the pricing.
Okay.
So our current shaft power meter solution is on the market for about $15,000 for the hardware installation. The Datum Hawk shaft power meter, which is way more advanced, will come at a premium. We haven't talked about the specific pricing yet, but it will be in the range of 20 to 30,000 for the hardware installation. But I can't say much more about that right now. But however, accommodations can be made to existing customers. So if they already have our shaft power meter, discounts can be made in order to upgrade to the newest one. So we are taking this into account.
Okay, so William Gu is asking about the effect of weather. I guess this is a similar thing to the shaft, the propeller fouling, that if these are things which make it much harder for the propeller to move through the water for the same torque. Is that
Yeah, the thing to understand in this is that the effects of weather on the ship are very slow to are very slow in compared to the measurements of our meter. So our meter takes up to 2,000 samples per second, and an averaging takes place to account for any vibrations and any other interferences that might happen at the same time. And the effects of the weather are so slow that they cannot be observed in the measurements. So they do not have any negative effect or any negative impact on the outcome.
Okay, I mean, if there's a current that's making it very hard for the propeller to turn, that would something that would show up, wouldn't it? Or,
yeah, that would show up on the torque and thrust measurements, but it wouldn't have a negative impact in terms of producing an invalid result, let's say.
Oh, very good. So back to Rodion, he's asking about different fuel types. I suppose it doesn't make any difference if they're still using a combustion engine, so there's the same technology would work for different engines. Is that something you want to?
We haven't looked into dual fuel engines yet. So this, first of all, the shaft power measurement solution is available for all engines, regardless of the fuel. So because it goes onto the shaft of the engine, it just measures torque and power. If we want to take it a step further and use the thermodynamics digital twin, at this point of time, we have only developed it for diesel engines. So we haven't accounted for dual fuel engines or engines fueled with ammonia, future engines, let's say. But this might be in our plans in the near future to do this. But as it is, the shaft power measurement solution goes into every vessel.
Right, very good. So Nick Smith is asking about. Nick Smith is from Greenpeace. He's asking about your ongoing support contracts, software updates, and recalibrations. I guess that would be sort of standard thing a supplier would do. Do you want to say anything about that?
Yeah, if I understand the question correctly, updates and software updates and stuff like that will happen every time a new iteration will be made. So I'm not the expert to talk about this, but we already provide our customers with updates on the software or our solutions. So yeah, this is something that we already do.
Okay, so if we go to Shahbaz Beg, who's a project analyst with OSM, so he's asking about whether the ship is loaded or unloaded. So I suppose his important point here is that the connection between the engine and the torque has nothing to do with anything else apart from the engine, but it's the other factors will shape how much the ship actually moves.
So yeah, the main takeaway is that this is, as you said, between the engine and the shaft. Nothing else is important. So it doesn't matter if the ship is loaded or unloaded. It doesn't matter what type of vessel it is. It doesn't matter how quickly it goes, how fast it travels. It doesn't matter if there is weather outside, heavy seas, stuff like that. This solution is able to take measurements in regards to the engine of the vessel, and this can be done for any vessel at any time, any operation.
Okay, so Rodion is asking about the baseline. Where does it come from? And if it's a very old date vessel, you wouldn't have the data about what the engine looks like in perfect condition, I suppose, would you? But do you want to talk about where you get the baseline from that you're comparing with?
It came from a vessel using an Artiflex two-stroke marine diesel engine.
Okay.
It was an older engine. I don't have the details of that, but I can provide them via discussion with that person later through email if he wants more details about that. So if that's for everyone, I suppose, that if everyone wants to get a bit more technical, and if they want from me to provide more information about something, we can come in contact through email and ask me whatever they want. And maybe if it's a sales question, I can direct them to the sales team. If it's an installation question, I can direct them to the installation team. This can be done easily.
Okay, so Konstantinos Athanasiou, who's a technical lead with Kongsberg Digital, he's asking about the support you provide. We kind of touched this before, but do you want to say you're helping companies calibrate it? You don't just sort of sell this and walk away. I imagine you help them get it working in a.
No, we don't walk away for sure. First of all, we have to calibrate this concept, the procedure, to produce correct outputs. And after the calibration, depending on what the customer needs and what they're willing to pay, we can provide the subscription. We provide subscription fees that include the ability from our side to collect the data and analyze them for their part. So, if something along the line breaks down, we have the ability to go on board and fix it. So yeah, we provide support throughout the life of the monitoring system.
Okay, so we've got a commercial question from Nicholas Bialy-Stocky. I don't know if you're able to answer this or it's secret, but he's asking how many vessels already have Datum torque meters. I think Datum's been making torque meters for a long time, but I don't know.
Yeah, I believe it's about something about 500 vessels so far.
Okay, very good. So Yoshio Otagaki, who's an advisor with the Ship Data Center, he's asking about scuffing, which I just Googled to see it means when things aren't lubricated properly or the metal is sort of dragging. You probably know a lot more about that than I do, but I guess it's detecting anything that's stopping the full power of the engine transferring to the shaft. So I suppose it would it?
So if the question is about if we can detect this?
Yeah, scuffing. Do you know what scuffing is? Because I just used Google. I don't know.
To be honest, I haven't heard about scuffing before, but I can say that we don't actually measure the lubrication properties of the engine. But if something wrong is happening and the power is reduced, this will show on the live measurement. So upon further investigation on this measurement and the data produced, we can identify the degradation, like improper lubrication of the cylinders and stuff like that.
Yeah, Google says scuffing is wear from scratches or surface deformation. So I guess that's the sort of thing that happens to an engine over time. And
yeah, that has an effect on the engine performance, so it will show on our data.
Oh, that's fantastic. Well, no more questions. I've got a few of my own. You said it was maintenance free earlier on. I guess there's no moving parts connecting the shaft with the meter. That's why nothing needs.
Well,
there's a question about Rodion just coming about recalibration. Yeah. Actually, I suppose that's a form of maintenance, but perhaps you meant the equipment maintenance. Did you?
Yeah. So to answer your question, apart from the stuff that is glued and bolted, not bolted, it's the wrong word, but glued onto the shaft, which are rotating with the shaft, there is nothing else that's moving. So everything is static. And as I said, it's maintenance free. So after the installation, we hope that there will be no more requirements for maintenance. So unless something goes extremely wrong, which hasn't happened in the past. So yeah.
Yeah, that's fantastic. And then do you want to talk about recalibration? I guess you're using the system comparing to the perfect model, so maybe it doesn't need recalibration, does it? Or does it need?
Sometimes, depending on the installation process, we have observed some cases that might require recalibration at some point, but we provide guidelines for that, and we can do it ourselves if needed. But sometimes maybe the strain gauges are glued into the wrong direction, and they provide an incorrect measurement. But this is immediately fixed by our team. So and it's calibrated to account for this. So in general, there is no need for recalibration, but it's something that can be easily be done later on if needed.
Yeah, that sounds great. And just general knowledge, when do companies normally do engine maintenance? I suppose it's using the dry dock every 2.5 or 5 years. Is that so that they'd use this to plan if they need to do engine work during the dry dock? Or you said to fix things if you see an emerging problem. So is that
the engine maintenance is not happening just once every 2 years, let's say. There is a planned maintenance schedule for every vessel. And it's this schedule is describes the maintenance intervals of its components of the engine and its component of the engine room. So some intervals coincide with each other, but others don't. So you might change the oil filters at some point, and after 1 month, change something else. So there's not a direct answer to your question, because there are maintenance intervals of some 1,000 hours for every engine component. But usually the whole engine is inspected at every dry dock and repaired accordingly.
Oh, so we've got a good engineering question here from Waruna Amarathunga, who's the Deputy Chief Engineer with Sri Lanka Ports Authority, but he's asking about shaft deformation, if you can detect that, and thermal stress analysis. I'm not sure what thermal stress analysis is, but you probably know.
We haven't included thermal stress analysis in our data yet, but shaft deformation, I believe, is something that can be observed. But I would like to have a look on that in more detail. And if the gentleman wants to have a detailed discussion about this later, we can have an email chat and address his questions more correctly.
Yeah, I mean, it's all about the whole system you're measuring the performance of. I suppose if the shaft is deformed, that will come through in the torque.
Yeah,
I suppose somewhere you're not going to get the.
It's not that simple. I
Okay.
mean,
Yeah.
But yeah, essentially, any deformation and any other fault on the shaft will have an effect on the measurements. It is a matter of how do you take the measurements and interpret them into useful information. So it depends on the data analysis that you perform to see what's wrong.
Yeah, well, that's fantastic. Well, we've had some great questions and some great ideas. I mean, I think, yeah, if there's 20% performance loss and you can help prevent that, and that's ships using 100 tons of fuel a day, that's a phenomenal amount of fuel you're potentially saving, isn't it? So, do you want to give some concluding remarks, and then we'll finish, I think, if you like. Or what would you like to leave the audience with, or to contact you if they find out more of it?
What I would like for everyone to keep in mind is that this is a very simple solution for engine condition monitoring, and it's a part of our predictive maintenance strategies. It's a very cost-effective solution because we use just one sensor, the shaft power meter, to measure the torque, and then use it inside the software that we develop in-house to produce other outputs as well. It has integration capabilities with many other systems on board, and accommodations can be made for existing customers to get it at a discount price. So, and also it's available for any vessel, any vessel type, any shaft diameter, and it's very modular. So these are the main takeaways, and the goal is ultimately to reduce downtime by identifying engine degradations and increasing fuel savings by identifying inefficiencies of the engine. So I would like to conclude with that. And if anyone has any more questions, or if he wants more details on the stuff that we do, they can contact me directly, and we can have a conversation about their issue and their question. And I would like to thank you for hosting this event, Karl, and the digital ship. It was a pleasure of speaking here. And yeah.
Oh, well, thank you very much. I think once again, we've shown a whole new story about a new way to improve how shipping works with digital technology. And I shall pass back to Neff for the closing words. Cheers.
Yeah, thanks, Karl, and thank you, Kostas, for that in-depth analysis. Thank you for your time as well. And I just want to let the audience know that we will be giving your email and the follow-up email with the webinar material. So yeah, any questions that weren't fully addressed will be you can follow up on that. So let me just remind everyone that we hold webinars regularly on Tuesdays and Thursdays. We have one coming up this Thursday. So yeah, keep in contact with us on our websites or on LinkedIn. And yeah, thank you very much for everyone.
Yeah, cheers. Bye-bye.
Take care.
Thank you guys. Bye bye. Take care.